Hello students, welcome to the physics classroom. Today we are going to discuss the principle of conservation of momentum. The principle of momentum conservation. The principle of momentum conservation. The principle says that the total momentum before collision is equal to the total momentum after collision. So we can state it in different ways. Number one, we can say the total momentum before collision is equal to the total momentum after collision. All right, that's the principle of conservation of momentum. You can also state this as the total momentum before separation or explosion. Explosion is equal to the total momentum after the separation or explosion. Okay, so these are the statements of the principle of conservation of momentum that we are going to apply in this lesson. First of all, we need to understand the condition under which these statements are true. Condition. The condition is that the net external force must be 0. Net external force must be equal to 0 newtons. If we are doing our experiments, for example, on a flat surface like this one, and we are talking about two objects colliding, we have one car A, colliding with maybe car B. Upon collision, after collision here, we see that they actually move together. Maybe they got coupled, maybe they coupled. So A, B, and this is A, B. So this could be considered before collision, and this is the after collision. After collision. So what you are saying is that the net external force must be 0. That's the condition. So in this case, we need to consider that no friction on the surface. Then the principle of conservation of momentum will work. No friction on the surface. And 2, the surface must be level. The surface must be horizontal. Let's say horizontal. Yes, we don't want the surface to be tilted. It has to be horizontal. In that case, then we can say gravitational force. Magnitude of gravitational force will be magnitude of the support force on the cars resting on there. So what you are saying is that if there is a force downward here, balancing with the scalar force, these forces should actually balance out, giving out the net external force of 0. This balances out with this one. And if there's a force here, Fg, it has to balance with the force Fs here. If there is a force here, Fg, and Fs here, they must balance. For that to be the case, our level, the surface level we are talking about here, must be horizontal. If it is horizontal or level surface, at the same time there's no friction on the surface, then we are sure that the net external force is equal to 0. then we can actually apply our conservation of momentum principles. Just to remind you, number one says that the total momentum before collision must be equal to the total momentum after collision, or the total momentum before separation or explosion is equal to or should be equal to the total momentum after separation or explosion. We are going to look at examples to make sense of this principle of conservation of momentum. The first example relates to an 8-kilogram car. We consider an 8-kilogram car. So again, it's a flat surface. We don't want any external forces, so we have to talk about flat surface. Consider a car. This is a car here. It has a mass of 8 kilograms. It collides with another car that has a mass of 5 kilograms. And this car, the 8 kilograms car, is moving at a velocity of 1 meters per second, 1 meters per second. And this car is at rest, 0 meters per second. Now they collide, and after collision, this is a collision line. They collide somewhere there. After collision, this is what we see. After collision, we're going to draw them on a separate line. This is the first surface here. And the same surface, but just want to draw the collision now here. So upon collision, the heavier ball moves at 0.5 meters per second. We see that after collision, this 8-kilogram mass, 8-kilogram mass moves at a velocity of 0.5 meters per second. But we do not know the velocity of the 5-kilogram mass. So we have to put 5 kilogram here, 5 kilogram, but we don't know what will be the velocity of that car. Here we have almost all the information. This is the before collision situation, before, and this situation I have drawn here is after. So we see after collision. The question is, how fast will the 5-kilogram object be moving? To answer that question, I need to actually calculate the momentum for each car before, and then I can also do the same for the momentum after. Then I compare total momentum before collision to total momentum after collision. Let me use a different marker. So the momentum of this car here, the 8-kilogram car, will be just 8 kilograms times 1 meters per second. So if I multiply the two, I'll end up with 8 kilograms meters per second. And the velocity of the 5-kilogram car, this one, sorry, the momentum will be 5 kilograms times 0. That will be 0 kilograms meters per second. And the total here, P total, the total momentum here will just be 8 kilograms meters per second, because I'm trying to add these numbers, this number and this number. If I add those two numbers, the answer is 8 kilograms meters per second. Now, after collision, for the 8-kilogram mass, 8 times 0.5, that's 4 kilograms, and then meters per second, because 8 times 0.5 is 4 kilograms meters per second. Then that will be the momentum of this 8-kilogram car after collision. The momentum of the 5-kilogram car can be written as 5 kilograms then times V, because we don't know how fast that will be moving. So we just do that. Now we have two numbers we have to actually add. We have here we added here, and here we should also add to have the two momenta. So what we are saying is that we have an equation that says, oh, this is P after P after, P total after, P total before. This is the, let me see, maybe I should say P total as well. P total is equal to this one, and P total here is equal to this one. So according to the principle of conservation of momentum, the 8 kilogram I got, 8 kilograms meters per second, this one must be equal to this entire of this, which is 4 kilograms meters per second plus 5 kilograms times V. All right. Then this equation I'm writing because of the conservation of momentum. I'm justified to do that. Now, if you can solve this equation, you can get the value of V. So let's try to solve the equation on the next page. The equation says what? The equation says that 8 kilograms meters per second is equal to 4 kilograms meters per second and plus 5 kilograms times velocity V. These are like terms, so I can transfer this one to the right hand side to become negative. So it will be like 8 kilograms meters per second minus 4 kilograms meters per second is equal to, I'm remaining with this, 5 kilograms times V. Now this will give me 4 kilograms meters per second equal to 5 kilograms times V, where V is the velocity of the 5 kilogram car after a collision. Divide both sides by 5 kilogram to find V. 5 kilogram both sides. A kilogram and a kilogram goes, 5 and 5 goes, a kilogram and a kilogram goes. So you end up with 4 over 5 of a meter per second. So 4 over 5 meters per second equal to velocity. And this is actually 0.8 meters per second equal to velocity that we are looking for. All right, so that's how we solve this problem. Let's take a look at second problem. Let's look at another problem. Another problem relates to an 80 kilogram person. So there is an 80 kilogram person. This person actually has a ball here and is standing on icy surface. So this is our icy surface. As you can see, we are using the horizontal surface to make sure that the net external force is 0, so that we can use our principle of conservation of momentum. The mass of the person here, mass is given as 80 kilograms, and the ball is given as a mass of 4 kilograms. And what's happening here is that the person tosses the ball at a velocity of, we are told that the ball is tossed at 20 meters per second. Ball is tossed. Ball is tossed. Let me write that one correctly. Ball is tossed at 20 meters per second. Okay, so there's a plus here, meaning that to the right, the ball is tossed at 20 meters per second, and the mass of the ball is also given 4 kilograms. Okay, the question is determine velocity of the man. Determine velocity of the man. Determine velocity of the man. Velocity of the man, person. Okay, so here we see that we have a conservation of momentum problem where we can also do the same thing. This is like the second idea. We said the total momentum before separation must be equal to the total momentum after separation. This is the idea that we are trying to use here. So total momentum before. So let's solve the problem. P total. So let's look at momentum of the man before. So I'll just divide this into two like this. This is before, and this will be after. Okay, I'll do that. So momentum of the man before is just 80 kilograms times 0 because the man is not moving initially. So that will be 0 kilograms meters per second. And then we have momentum of the ball. The momentum of the ball will be 4 kilograms times 0. The ball is not moving initially, 0 meters per second. And this will give us 0 here, meters per second. Total, so P total, before you have to add this and this. So we have the total momentum as 0 kilograms meters per second. That will be the total momentum before collision. After collision, what do we have? Well, momentum of the man will be 80 kilograms times velocity v. We don't know how fast the man will be moving. That's what we are looking for. And momentum of the ball will be 4 kilograms. That's the mass of the ball. Then times what? Times 20 meters per second to the right. So positive that. That gives us 20 times 4, it's 80 kilograms, and then meters per second. The total here, P total, will be this plus this. That's the total momentum after collision. So that gives me the total momentum. So I'm going to write it like this: 80 kilograms times V plus 80 kilograms meters per second. I cannot add the two because this one has velocity in it. So they are not the same numbers, so I cannot add the two. This is my momentum, total momentum before separation. Let me use a different marker. Total momentum before separation, total momentum before separation, sorry. This is after separation, this one, and this one is before separation. So if the conservation of momentum is correct, let's read it again. The conservation of momentum, point number 2, says that the total momentum before separation, in this case, separation between the man and the ball, must be equal to the total momentum after separation, as long as the net force is 0. That means ignore friction. The man is standing on ice, so we can actually equate these two expressions. So basically what you are saying is that 0 kilograms meters per second must be equal to what? Must be equal to 80 kilograms times V plus 80 kilograms, then meters per second. We want to find V, this V here. So I'm going to transfer this to the right-hand side to make this one minus 80 kilograms meters per second equal to 80 kilograms times V. Then I'll divide both sides by 80 kilograms because I need V to be on one side of the equation. I divide by 80 kilograms on both sides. This kilogram and kilogram goes, 80 and 80 cancels out. A kilogram and a kilogram goes, 80 into 80, it's just 1. What do I have? I have velocity is just minus 1 meters per second. So the velocity of the man is 1 meters per second to the left, 1 meters per second to the left, That's why we have a negative sign there, to the left. All right, so that's the answer for that one. Let's look at two more problems. This problem says that we have a 5 kilogram crate moving to the right at 0.3 meters per second. So this problem says that we have a 5 kilogram crate, which is moving to the right at 0.3 meters per second. Of course, we do this on a flat surface, right? Oh, it's a crate, so let's remove that. We have the flat surface as usual. Then we have also a 3 kilogram crate, another 3 kilogram here, 3 kilogram crate, and this one is moving at to the, this one is moving to the left. So this is moving to the left at 0.5 meters per second. Okay. Now, what happens after collision? After collision, this is what we see. Oh, let me do this so I show that it's a surface. The surface. Now, what happens after collision? After collision, I see the 5 kilogram crate. 5 kilogram crate is actually moving backward. Is moving backward at a speed of 0.2 meters per second. The question for you is, oh, it's a crate, so sitting on the surface. The question for you is, what will be the speed of the 5 kilogram object? What will be the speed of the 5 kilogram object? We do the same thing. We do momentum for this. I'll just do it right here. Momentum for the 5 kilogram ball here be 5 kilogram times 0.3 be 1.5 kilograms meters per second. Yeah, 1 there. Is this clear enough? Let me see. I'm trying to do fast, but it doesn't help. 1.5 kilograms meters per second. Then the momentum of the 3 kilogram will be, no, look at this one. This is moving to the left. So it'll be 3 kilograms times negative 0.5. So it'll be 3 kilograms times negative 0.5 meters per second. So that will give us minus 1.5 minus 1.5 kilograms meters per second, close bracket. So if we move on to this box, what are we going to have? We are going to find the momentum of the 5 kilogram object as follows. Well, 5 times 0.2 is 1, but it's moving to the left, so minus. This will be minus. So that will be 5 kilograms times 0.2 minus 1.0, of course, 1.0 kilograms meters per second. The minus is because this moving to the what? To the left. And 0.2 meters per second will be minus, just like what we did previously. Okay, now for the 3 kilogram object, this one, the momentum will be 3 kilograms. We don't know the velocity, so put just V there. Okay, to find the total momentum at the beginning, we add here, and here after our collision, we add here also. So what do we have? P total before collision, P total here will just be 0. See this? Because 1.5 kilogram meters per second plus minus 1.5 kilogram meter per second, 0 kilograms meters per second. So we have 0 momentum before collision, and after collision, we have this expression. If the principle of conservation of momentum is correct, then we can equate the two. 0 kilogram meters per second must be equal to minus 1.0 kilograms meters per second plus 3 kilograms velocity here, V. Okay, then I can transfer this to the right hand side. It will look like what? It will be just 1.0 kilograms meters per second equal to 3 kilograms times V. I can divide both sides by a kilogram, and the kilogram goes. I remain with 1/3. So V is just 1/3 meters per second. So the velocity of the car will be 1/3 meters per second. Okay, our last problem. Let's look at the last problem. We have enough pages. Yep, last problem. In the last problem, we have a 2,000 kilogram car. So let me draw it here. A 2,000 kilogram car. This is 2,000 kilogram car is moving at 10 meters per second. And what do we see? It collides with a vehicle at rest. It collides with a vehicle at rest, but this vehicle has a mass of 1,333 kilograms. Okay, and the velocity is at the rest. So this is happening on a flat surface. Remember, we use a flat surface so that gravity cancels out with support force, and therefore the net force will be 0. Now, upon collision, I'm going to redraw my surface here. Upon collision, these two cars actually they couple. Somehow after collision, they do couple. They become like one. Become like one, and they move at the same velocity. V, we don't know how much that is. So it's still 2,000 kilograms, and this is 1333 kilograms. Okay, so the question is, what will be the velocity of the coupled cars upon collision? What will be the velocity of the coupled cars upon collision? We do the same thing. We're going to find momentum for each. For the 2,000 kilogram car, that would be 20,000. 20,000 kilograms meters per second. And the next one plus this one will be what? 1333 time, this is kilograms, and then times V. Well, V is 0, so wait a minute. That becomes 0. So just 0 kilograms meters per second, right? This became 20,000 because 2,000 times 10 is 20,000. This is 0 because 1333 times 0 is 0. So that will be momentum before collision. And if you want to find the P total, well, that comes out easily to be what? 20,000. So 20,000 kilograms meters per second. Okay. And the after collision, well, look, the momentum of this will just be 2,000 what? Kilograms times V. Momentum of this one will be 1333 kilograms times the same V, because they're moving at the same velocity. Same V here, same V here. Now, if you want to add to find the sum, you do that. Then the total, P total after collision, it will just be, let's add the two. What do we get? We get 3,000 and 333. Yeah, 3,333. That will be, whoa, yes, times V. All right, so times V, like that. Sorry, kilograms times V, like that. Or you can just add the masses together and then times V. If that would be maybe easier for you, just add 2,000 kilograms plus 1333 kilograms, then times V. I don't have enough space here. Times V. There's a V here. So small, yeah. If you do that, if you add the two here, you get 3,333, and then a kilogram times V. All right, so if conservation of momentum is to be observed, let me use different marker. Then this momentum here, which is the total momentum after collision, must be equal to this momentum here. So we are going to equate the two. We are going to have 20,000 kilograms meters per second must be equal to 333 kilograms times V. Now to find V, divide both sides by 3,333 kilograms, divide by here 3,333 kilograms. This and this cancel. This and that, how much would that be? Let me see if I have a calculator here. But I believe that must be, this is 20,000 divided by 333. So let me get my calculator quickly and see what I get. Okay, so we are dividing 20,000 by 33. Oh, I got 6. So that is 6. So V is 6 meters per second. So that will be the velocity of the coupled cars, 6 meters per second. All right, thank you so much. I'm sure you have found this video useful. The idea is just to realize that you need to deal with momentum, be able to calculate momentum for each involved object, add up the momentum to find the total momentum before and equate to the total momentum after. It could be a collision, or it could be a separation, or it could be an explosion. The idea is the same. We do see a separation when a cannon machine fires a cannonball. That's an example of a separation. Or a gun shooting out a bullet. That's also an example of a separation. So these problems can be either collisions or separations. But remember, these are the conditions where the conditions are here. The net external force must be 0. Usually these problems, they do say that ignore friction, or they say the collision is happening on a flat surface. That's what they say. That's a green light for you to use the principle of conservation of momentum. All right, I'll stop here. If anything, you'll let me know. Bye for now.